Hey everybody, hope you're having a great day. Today I'm going to be talking about how light absorption occurs, and this will be the first part to probably a three-part series. First we're going to consider the Lorenz oscillator and simple harmonic oscillation, and then we're going to include damping in our oscillation, and that will be part 2, and then we're going to include a driven damped oscillator, and that will be part 3, and there we will see an equation that really gets at the heart of light absorption by an atom. Okay, so who was Lorenz and what was his oscillator? In a previous video I said first let's consider a ball of neutral space, but it's actually a positive and a negative charge really close together. We just can't tell. And then let's switch on an electric field, okay? That electric field is going to induce a dipole, so it's going to split the charges up. Plus is going to be up here, minus is going to be down there. And they're going to separate by a distance, let's call it d. Now, if we just turn that electric field off right now, well then here's what's going to happen. These charges are attracted to each other, so they're going to start approaching, but they're going to be approaching so fast that the positive charge is going to pass the negative charge, and they're basically going to switch positions effectively. And after that happens, well, it's just going to repeat again. So positive is going to switch positions with the negative again, and that'll just keep happening. Same way that a ball on the end of a spring oscillates back and forth. And that oscillation back and forth is called simple harmonic motion. Eventually it dies down because there's friction in the spring and in the air and various sorts of things, and that is called dampening. But we're going to not consider dampening in this video. So effectively, our charges are just going to keep oscillating back and forth for all of time. So, Lorenz thought that this oscillation was simple harmonic, and therefore it can be described by Hooke's law, which says that the restoring force, F, is equal to some spring constant, negative k, times the displacement d. Now, you might wonder, well, the force between this positive and negative should be the Coulomb force. Well, yes, it should, but if we assume Coulomb force, then that's going to make the differential equations a lot harder to solve. So we're just going to consider this case, which this Lorenz guy considered, and it turns out it works pretty good, and he was a very smart guy. He was a 19th century physicist, and he also did work in a lot of areas, but he's a lot smarter than me, so I'm going to trust him and not try to do all this on my own, since he already did all the hard work. Okay, so this is what Hooke's law said, and we said this was the restoring force. That's very important to keep in mind. It's not the force we applied in the first place. It's the force that basically brings this positive charge back to this negative charge. The restoring force. And now, Newton's second law what's that say? That says F equals ma. That says that our force is going to be equal to our mass times our acceleration. We can rewrite the acceleration as the double derivative of the position with respect to time. Now this d up here, we can rewrite it as x minus x naught, where x naught is the spring's position at time 0, basically before we applied the electric field. Well, we can just set that equal to our origin, so we'll just say that's 0. Therefore, we can rewrite this as kx. And that's probably the form most people are familiar with, seeing this as an x instead of a d or something similar. Well, now we have a force is equal to negative kx, and we have the force is equal to this. So we can combine those and say that m times the double derivative with respect to time equals negative kx. I can add kx to both sides, get m double derivative of x with respect to t plus kx equals 0, and then I'm going to divide by m. And we get plus k over m x equals 0. This is the equation for a simple harmonic oscillator. And this is probably one of the most, if not the most important equations in all of science and physics and engineering and other fields. It explains, partly, light absorption. It explains the way sound propagates through air, sound waves. It explains pendulum motion. It explains kids swinging on a swing. And explains all sorts of other phenomena. So in my opinion, if you had to choose one concept and one equation that explains mostly everything in the universe, the simple harmonic oscillator is it. So it is very important to know and have a deep understanding of the simple harmonic oscillator, in my opinion at least. Because I've seen it over and over and over again throughout my education. And it just keeps coming up. Anyways, let's get back to it. So we have a differential equation here, second order, linear. Now we're going to solve it. If you've taken differential equations before, you know this is going to be a piece of cake to solve, but if you haven't, don't worry. As long as you know how to take derivatives, this is going to be pretty easy to solve. So we're going to have a few solutions here. One solution we can write as x equals a sine omega t minus phi. And I'll prove to you right now this is a solution. We take the first derivative, we're going to get a cosine. We bring the, I wrote omega here. Okay, so right here I'm going to call omega equal to the square root of k over m, just because I'm going to have to keep writing this k over m. So to keep things faster, I'll write it as omega. And I'm cheating a little bit because there's actually a reason why you write omega, because it's the frequency of the oscillator. We can also write omega squared equals k over m. Okay, so that means I would have to bring the omega out here. So, a omega cosine omega t minus phi. That's the first derivative. Second derivative is equal to negative a omega squared sine omega t minus phi. Now, this is our second derivative. Our equation says our second derivative plus the km times the original solution should equal 0. Well, let's try that out. So we got negative omega squared sine omega t minus phi plus k over m. Our original solution was a sine omega t minus phi. Well, if we just rewrite k over m as omega squared, which we said there, then we got that, and these are the same thing, so they equal 0. Check, that is indeed a solution. Another solution is b cosine omega t minus phi. These a's and b's are just some random constants. So let's check this quick. We got a prime equals b negative b omega sine omega t minus phi. The double derivative equals negative b omega squared cosine omega t minus phi. And this is going to equal to omega squared times that. It's all equal to 0. So that's also a solution there. Now, an important theorem in differential equations says any general solution can be written as a linear combination of specific solutions. So we have specific solutions here, and so in other words, that theorem says we can write a general solution, x, is equal to a combination of these two we just had. So a sine omega t minus phi plus b cosine omega t minus phi. And to redo our notation again, we're going to write this in the form E equals negative I omega t, because this is how physicists like to write their, well, sines and cosines basically. And I can prove to you this is also a solution. It's pretty much just, it means A has an imaginary number in it, and well, that's basically all it means. It does satisfy this equation, because this is equal to cosine omega t minus I sine omega t. So that we see, well, this phi would be equal to 0, b is equal to 1, a is equal to negative I. So yes, same thing. But I think this is easier to take derivatives of. So let's do that on the next page. We said x equals e negative I omega t, therefore x prime equals negative I omega e negative I omega t, x prime prime equals negative I omega squared e I omega t negative I omega t. Okay, and then negative times a negative is a positive, I squared is a negative, so negative omega squared e to the negative I omega t. So our double derivative, negative omega squared e to the negative I omega t, plus omega squared times our original solution equals 0. Yes, that's true. Check, that's a solution. Okay, so now what we're going to do is plot this and show that it does describe realistic behavior. And I only write it in this e to the negative I omega t form to make the previous parts of the video easier and the notation more compact to understand. Okay, so we're going to plot this here. This is our time axis. This is our axis, x of t. We'll call this position up here A. Let's just consider the solution A sine omega t. That way we wouldn't have to try and think about superimposing sine and cosines. At time t equals 0, well, a sine wave is at 0, and then it approaches A, and it reaches A when the time is equal to, let's see, this is max when omega t is equal to pi over 2. So when t equals omega over 2, no, when t equals pi over 2 omega. So this is pi over 2 omega there. And then goes back down to a minimum at pi over omega. Not a minimum, but it crosses 0. Then it goes to a minimum at pi over 3 omega. And it just repeats this behavior for all of time. So, this is just, well, I guess in this case we would have to shift our whole wave over so that at time 0 we had the displacement A, which I really should have just called D. Because originally, remember, our positive and negative charge was separated by a distance D. And that's what's signified here. So let's pretend this is our t equals 0 right there. So we switched on our electric field, we're here. Then we turn it off, and then the positive and negative is going to be approaching each other. And here they're going to be exactly aligned on each other. But since they were accelerating towards each other, Well, they can't just stop instantaneously. They're going to pass each other. And then right here, it's going to look like negative there and a positive there. And then it's going to repeat the process going back. You're going to positive and negative are going to be really close. Here they're going to be on top. So on and so forth. I think you see the trend. Okay, so that is the Lorenz model of simple harmonic oscillation in an atom, effectively. I think that's all I wanted to say, so thanks for watching. Hopefully I'll see you in part 2, and have a great day.